Okay, so in this example we have a disk rotating with a constant rate omega 1 with respect to the arm OC, and we also have told that arm OC rotates about a fixed vertical axis with a constant rate omega 2. We're told that the observer and the little xyz axes are attached to the disk, while the capital xyz axes are fixed in space. We're given indication that at this instant the capital and lowercase axes are aligned. Based on this information, we're asked to find the angular velocity of the observer, as well as the angular acceleration of the observer. Okay, so the way I'm going to solve this problem is I'm going to note that the angular velocity of the rotating frame, or the observer at this instant, results from the superposition of two rotations. We first of all have the rotation rate omega 2, and that is about a fixed axis in space, which I'm going to designate with the unit vector capital J. And I'm going to superimpose on this a rotation which is actually clockwise positive, so I'll write this as minus omega 1. And the direction for that, given it's clockwise positive, is actually going to be, in this instance, the little k, where little k, of course, designates the fact that that rotation is about a rotating axis. Now I'll come back and express that in a consistent vector set in a moment, but before I do that, let me go ahead and compute alpha, the angular acceleration of the observer. So in this regard, what I can do is say that alpha is going to equal omega 2 dot in the capital J, plus omega 2 in the capital J dot. Of course, I'm just using the product rule of differentiation here, minus omega 1 dot in the little k, minus omega 1 in the little k dot. Now if I go back up into the problem statement, you'll see that both omega 1 and omega 2 are constants, which indicates that the first and third term here go away. Likewise, we know that the capital J unit vector is one which is fixed in space, which means the second term goes away because the time derivative is of 0. This leaves us with an angular acceleration which is equal to minus omega 1 times k dot. We keep in mind that the time derivative of a rotating unit vector is omega cross itself, so we can express this as minus omega 1 times omega cross k. If we go ahead and do some substitution here, this is equivalent to minus omega 1 times quantity omega 2 in the capital J, minus omega 1 in the little k, crossed with the little k. If I expand the cross product here, I'm going to need to note that the axes are aligned at this instant, and so if I do that, I can replace the little k with capital K's. And if I do that, I'm going to end up here with the result, minus omega 1 times omega 2 times quantity capital J cross capital K. You'll note that I've thrown one term away here because I know a unit vector cross itself is 0. At this point, I can go ahead and work out the final answer here. Capital J cross capital K is capital I, so I'll have minus omega 1, omega 2 in the capital I. And up above here, if I now want to put this in a consistent unit vector set as well, I'll have omega 2 in the capital J, minus omega 1 in the capital K. From here, all you need to do is plug in numerical values. I know you got this one. Best of luck.